Good morning to all. Today we'll discuss about chapter number 7, frequency domain analysis. In this chapter we'll discuss about frequency response specifications. What is the correlation between the time and frequency domain response, and body plot, stability analysis using body plot. We'll discuss what I mean by frequency domain and what is the introduction or brief introduction about the frequency response. In time domain analysis, a system to various input like step input, ramp input, parabolic, all our functions are with the time and studied the transient and the steady state response known as the time response of the system. In the chapter number 5, we discussed about the time response specifications. In that we have given a different types of the input like a step, ramp and parabolic, and we have discussed about a steady state error and the transient error with respect to the time domain specifications. By frequency response, the steady state response of a system is subject to sinusoidal input. In frequency response method, we vary the frequency of input signal over certain range and study the response. The magnitude and phase relationship between the sinusoidal input and the steady state output is known as the frequency response. Here it is, we have shown one diagram. Here it is, what kind of input we have given the sine as an input and what kind of output we are getting. There are different types of the techniques. With the help of that we can understand the frequency response. First one is a body plot, second one is a polar plot, and third one is a Nyquist plot. In our syllabus we are going to discuss about only with respect to the body plot. Next, this frequency response plot is used to determine the frequency domain specifications and to study the stability of the system. Here it is, as I told you, we are going to discuss the body plot in this chapter and we are going to find out the stability of the system with the help of the body plot. Then what are the advantages of the frequency response techniques? The first advantage is it is very easy to get the frequency response test in the laboratory with a good accuracy. Second, effect of noise disturbance and the parameter variations are easy to visualize in frequency response. Means we'll get a frequency response. With the help of that it will be easy to analyze the different parameters. Third advantage is the apparatus required for measuring the frequency response are easy to use and simple. But there is one limitation for the frequency response. It requires a fair amount of time for drawing the frequency response. Already we have discussed the time response specifications. Here it is, we'll discuss some frequency response specifications. Here it is, input is shown and the output is here. Omega is and the MR is the peak resonant, and this is the response. Bandwidth is between 0 to whatever the wherever we are going to get the steady response, that whatever the band is there, that is called as the bandwidth of the frequency bandwidth. Next, this is actual plot for the magnitude plot and the phase plot. This magnitude plot and phase plot we are going to draw on a semi-log paper. But to understand the specifications, here we have shown the magnitude plot and the phase plot. Magnitude plot, it's considered from the 0 dB, and always we are going to consider the logarithmic value with respect to the magnitude plot and the phase plot. Magnitude plot 0 dB, and here it is whatever the omega gc and omega pc is nothing but a frequencies with respect to the magnitude plot and the phase plot. We will discuss one by one specification with the help of the frequency response. First one is a resonant peak, MR, and that is nothing but the maximum value of the magnitude of closed loop transfer function is called as a resonant peak, as shown in this diagram. Second one is omega r, whatever the particular frequency at MR is nothing but a resonant frequency omega r, shown in this diagram. Next, bandwidth, it is a frequency at which T transfer function of j omega drops to 70.7% from its frequency value. The range of the bandwidth is 0 to omega b, as shown in the diagram. Here it is. 0.7, it is marked omega b, and horizontal line is marked for the 0.7, not 7 means 70.7%. Whatever that particular band is nothing but a bandwidth. Next definition, cutoff frequency. The frequency at which the magnitude of closed loop is 3 dB from its zero frequency is called as a cutoff frequency. Next, cutoff rate. The slope of log magnitude curve near to cutoff frequency is called as cutoff rate. Next definition is phase crossover. These are the important definition with respect to the Bode plot. A phase crossover omega pc, the frequency at which the phase margin is minus 180 degrees is called as a phase crossover frequency. We'll see in the diagram. Here it is omega pc. In the magnitude plot, omega pc, once we'll draw the phase plot, we have to mark the 180 degree over there, and we have to draw the vertical line up for the magnitude plot, and wherever that 0 dB crosses, that is nothing but a omega pc. Next one is the omega gc, gain crossover frequency. The frequency at which the magnitude of gh of j omega is a unity, it's called as a gain crossover frequency. 20 log of 1 is a 0 dB. Next one is a gain margin and phase margin. We'll discuss one by one. Gain margin is defined as magnitude of reciprocal of phase crossover frequency omega pc, which is the frequency at which the phase is minus 180 degree, and the phase margin is, it is defined as 180 degree the phase angle phi 1 of open loop transfer function at unity gain. We'll see the gain margin and phase margin in the diagram. After drawing the phase plot, if we'll mark that 180 degree line and the vertical line up to that 0 dB line, up to above that, whatever the particular line is there, that is nothing but a gain margin. And after drawing the magnitude plot which will crosses the 0 dB, we have to mark a vertical line for the phase plot, and whatever the difference in between the constant value and the phase margin, it's called as the phase margin. Minus 180 degree and the constant value is nothing but a phase margin. We'll discuss in the example, because for each example we are going to draw this magnitude plot and phase plot on the semi-log paper. Next we'll discuss about the correlation between the time domain and the frequency domain for a second order system. This is very important from exam point of view. This question is for 4 marks. Firstly, we will consider the simple or general standard closed loop transfer function. Everybody knows that C of s upon R of s is equal to omega n square divided by s square plus 2 zeta omega n s plus omega n square. Here it is, we are going to discuss what is the relationship between the time domain and the frequency domain. Then for that purpose, we'll put j square is equal to minus 1, as we will cancel the imaginary term from that, and then we will divide it by omega n square. First we will put j square is equal to minus 1, therefore C of j omega divided by R of j omega is equal to omega n square divided by minus omega square plus 2 zeta omega n j omega plus omega n square. Only in the first term, wherever the j square omega square is there, we have put the value j square is equal to minus 1. Then we have divided by omega n square. So after division, we got the next step like this. C of j omega divided by R of j omega is equal to 1 divided by omega square divided by omega n square plus 2 zeta omega n j omega divided by omega n square plus 1. After division, finally we got it 1 upon 1 minus omega divided by omega n square plus 2 zeta n j omega divided by omega n. Just we have rearranged the terms. Then what we'll do, we'll replace omega by omega n by x. So C upon R for the j omega is, as we have replaced omega by omega n by x, 1 upon, in bracket, 1 minus x square plus 2 zeta j x. Then here it is, as we want to find out the magnitude For finding the magnitude of this transfer function C upon R, we have to consider and we have to use a formula under root of imaginary real part and the imaginary part square. So what is the real 1 upon root over, what is the real part? 1 minus x square is a real part, we have to take a square of that, therefore 1 divided by root over in bracket 1 minus x square square plus we have to take a square of imaginary part also, but we will not consider the j, therefore 2 square is 4 zeta square into x square is there. Then for find out the value for that at x which will maximize the magnitude, so we have to take a first derivative and equate it is equal to 0. So m transfer function t mod of that t transfer function of j omega is equal to first derivative, we have to take a first derivative with respect to x, dm upon dx is equal to. So before taking first derivative, we'll consider that whatever the root is there above that, you have to take it above that numerator at the numerator side, and minus 1 upon 2 is for the root, and then it will be easy for us for taking the first derivative with respect to x. Then here it is, we'll use the product rule here, dm upon dx is equal to minus 1 upon 2 into bracket 1 minus x square square plus 4 zeta square into x square raised to minus 3 upon 2, as we are taking the first derivative, into as there is a product, there is a we have to take the derivative of that particular term also. So here it is 1 minus 2x square plus x raised to 4 is there, plus 4 zeta square into x raised to 2. Then we'll equate it is equal to 0 and we will simplify it for x shown in the next step. We'll equate it is equal to 0 and simplify it for a x. So after simplification we got x square is equal to 1 minus 2 zeta square, therefore x is equal to root over 1 minus 2 zeta square. As in the last step we have put x is equal to omega upon omega n. In this equation also we'll replace x by omega upon omega n, therefore omega divided by omega n is equal to root over 1 minus 2 zeta square. Therefore omega is nothing but a resonant frequency, omega r is equal to omega n into root over 1 minus 2 zeta square. The resonant peak is obtained as for the MR we have taken this MR is equal to 1 upon root over, same formula we will use here, root 1 minus x square plus 4 zeta square into x square. We'll put value x square whatever we got in the last step, x square is equal to 1 minus 2 zeta square. We'll put in this MR is equal to, as we want to find out the equation for the MR also. Then MR is equal to 1 divided by, after putting the x square is equal to 1 minus 2 zeta square, we got the next step. We have to simplify it by putting that x square value. After simplification we got the MR is equal to 1 divided by 2 zeta root over 1 minus zeta square. It is very it's very simple to simplify this. Therefore MR is equal to 1 divided by 2 zeta root over 1 minus zeta square. Therefore for a frequency, in the last step we got the equation omega r is equal to, now in this we got the answer for the MR is equal to, then we can prepare a final summary for the time and frequency. As here it is, we are finding the relationship in between the time and the frequency domain. In a time domain, omega d is equal to omega and root over 1 minus zeta square, while in a frequency domain omega r is equal to omega n root over 1 minus 2 zeta square. Then peak resonant is in the time domain is mp is equal to, as we discussed in chapter number 5, mp is equal to e raised to minus pi zeta divided by root over 1 minus zeta square. And in a frequency domain, as already we have simplified this, mr is equal to 1 divided by 2 zeta root over 1 minus zeta square.